Okay. Hi, we're happy to have Bernhard Haeupler from CMU. So Bernhard has done his undergraduate in TU Munich, then he did his PhD at MIT. Then I think as a postdoc in Silicon Valley in the Microsoft, which I think doesn't exist anymore. Well, it happens. Then in Princeton.
Quit while you're ahead.
Yeah.
After Bernhard,
yeah. Quitted on time. Yeah. Then at Princeton, and finally is a professor at CMU. And Bernhard is working on optimizations algorithm and distributed algorithm, local algorithms, and tell us about congestion and shortcuts.
Thank you so much. So yeah, this is the last talk of the day. Thanks for staying here. I tried to make this, entertaining and interactive, and I kind of need your help for this, right? So there's gonna be lots of questions to be answered. If you have any idea, just help me out here. It's gonna make it more fun for all of us. So what I want to talk about is distributed algorithms and generally optimization algorithms. So take your favorite algorithmic problem like minimum spanning tree, shortest path, maximum flow or whatever, and you want to solve these kind of problems distributedly. And it turns out that if you really want to understand these problems, you need to understand something in a distributed setting. You need to understand things that are not just problem specific, but that are really specific to the distributed setting. And there's kind of a common theme. And so one thing that's particular about distributed systems, that typically computation is not the problem. Typically the bottleneck in distributed computing is communication. Okay? So there's a lot of information present in the system, and we want to compute something, and we can't just send around all the information. So what we need to do is we kind of need to aggregate. Any distributed optimization algorithm will have to aggregate information at some point of time. It has to think about how to, this thing is not properly working. It has to think about how to send around, which ways to route this information efficiently in this network. And it has to do so distributedly. Nodes typically don't know what the network structure looks like, what information is out there. You still need to find out how to kind of send this aggregate information around without knowing everything in advance. And so it turns out that if you want to design distributed algorithms, then thinking about these questions, thinking about how does this distributed information flow look like, is a much more important question than what's the specific structure of the problem. And I found this kind of surprising. So there's going to be a common theme and kind of some common understandings that underlies all of these things, and this is much more important than it plays a really important part in creating fast algorithms. So let's dig into this. So this is going to be a theoretical talk, right? So we're going to have a very clean, classical problem setting, which is just the classical congest model. Okay, so for all of you that have not seen this, network. What's a network? A network is just a graph for us. So nodes are our computers, and information is present distributedly, right? So nodes in the beginning only know their local neighborhood. Nodes only know the edges that are adjacent to them. And there's some kind of communication that's going on, so let's just, for simplicity, assume it's synchronous communication. There's communication rounds. In every round, every node, along every edge, I can send some limited amount of information just to make it clean and easy. Let's say log n bits per edge I can send in every round. Right? And computation is free. Right? So the bottleneck is really going to be communication. And then the question is, pick your favorite optimization problem. Right? From your undergrad algorithms days, suppose that they have edges, lengths on some weights on the edges, find the shortest path from A to B, compute a shortest path tree, compute a minimum cut in the network, or any question like this. And what do we try to minimize? We want to try to minimize the number of rounds that it takes to compute one of these things. Does the model make sense? Is that clear? Yeah? Awesome. Sweet. Okay, so what are trivial bounds that we can get for these kind of problem? Like how much time is it going to take me at least to compute a minimum spanning tree? Diameter, right? Because if I haven't even, information can only travel one hop per time, right? If I haven't seen the rest of the network, I cannot make a good decision. In a cycle, for example, I need to know whether the edge very far from me is something that closes the cycle and my heavy edge here, does it need to be used or not? I can only make this decision if I know about all the edges that are far away as well. Right, so there's some local problems like coloring and so on and so forth, which you can solve locally and you don't need diameter time. Those problems we don't think about. We want any non-local problem is going to take at least diameter time. Right, so any of these problems that we listed here. Great, so that's kind of a trivial lower bound. Whoa. Okay, what about a trivial upper bound? M, why? That's right. You can just flood everybody can just flood all the information that you have. There's order M information present in the system. After order M rounds, everybody knows everything and you can just compute whatever you want to compute locally. Right? So the interesting things happen kind of between M and D, where D is the diameter. And that's a big difference, right? So a typical networks that we're interested in, the diameter is, I typically think of it as, let's say, polylogarithmic. Right? Most natural networks will have a comparatively small diameter to the number of nodes. Maybe you have some diameters that's larger, but the diameter is never going to be polynomial in the number of nodes. Right? So that's a strange network. So there's a big difference between doing something in diameter time and doing something in linear in the number of nodes or linear in the number of edges time. Right? So our dream goal here is that we want to compute any of these optimization problems, ideally in nearly diameter time. Right? That would be awesome. That would be really great. And during the talk, I'm going to write these O tilde notation to basically ignore logarithmic factors. Right? So logarithmic factors we're not going to care about. So order D time would be great. Okay, so let's look. So it turns out that kind of the nicest and most instructive problem to look at is actually the minimum spanning tree problem. It's also the one that's been most widely studied. So let's look at it for the minimum spanning tree problem. Okay? So minimum spanning tree, I think everybody knows what the problem is, right? We have weights on the edges and we want the smallest number or the smallest weight subset of edges such that it forms a tree, right? You want to buy power lines, everything should be connected to each other, and we want to spend as little as possible. Okay, so what would be a good first attempt at a distributed algorithm that looks, reasonably distributed, reasonably parallel to compute an MST? Prim, so how does Prim work? Borufka, yeah. I mean, whatever the name is, right? So initially, every node knows its surrounding edges, right? And it's clear that the cheapest edge leaving a node is definitely going to be part of the MST. Okay. Since we want to do things in parallel, let's just every node marks the cheapest edge going out of it, and we already have a part of our MST, right? So that's great. And then how do we continue? Well, these edges are going to form some connected components, right? And each connected component is going to look, what's the cheapest edge leaving my connected component? Again, this has to be in the MST. We mark these edges. We're going to continue until we have an MST, right? Yeah, so this is Borufka's algorithm, but yeah, it's fairly straightforward. Okay, so the time that this takes. So yeah, how does this work? Initially, everybody marks the cheapest edge. Then we have these connected components, some passes, some trees. We mark the next one, and so on. In this case, we already have an MST. So how long does this take? Well, it takes. The overall round complexity is basically, the number of iterations times the time it takes for one iteration. That's simple. Can somebody tell me how many iterations it's going to take? Log n, why? I could not understand this. Log n is good, yes. Log n, why? Yes?
You can build it so that generation information so that you only join connected components that are approximately equal in size, and then each time you get a connection, each round, you only get connections that double the size of the connected components, and you end up with a logarithmic number of rounds.
That would work too. In fact, even if you do joins arbitrarily, it's fairly easy to see that the number of connected components halves every round, because every connected component is going to join with at least one other connected component. So the number of connected components goes down by a factor 2 in every round. After log n rounds, you're done. Great. Okay, so the number of iterations is log n, which is really, really small for us. So that's great. So how much time does it take for one iteration? Well, in one iteration, what do we need to do? We need to find the cheapest edge going out of our component. Right? So one easy way to do that is I'm just going to, within my connected component, I'm just going to flood around what the cheapest edge is. And then I'm done, right? Until everybody has heard it, then we're done. Okay, so how long does this take? It takes, well, diameter time. Right?
No.
No? Why not? O of n, why? No, there's not going to be any congestion because diameter is a component, yes. Which is, so yes, it's going to be a diameter time, but the problem here is when, order d time, that would be great, right? But in fact, it's going to take the number of rounds that it takes is going to be the number of, the diameter of a component, right? Which could be much larger than the diameter of the network, right? So it's maybe a little bit tricky to see at first, but it's, take a graph, take a subset. The induced graph on that subset could have a much larger diameter than the underlying graph, right? So it could be that the induced subset is just a long, windy path in an otherwise really small diameter graph. And if you stay within that component, it's going to take, it's going to take diameter of some component which is not related at all necessarily to the diameter of the graph. Right? So this order d here is wrong because, the diameter of a component has nothing to do with the diameter of the graph.
But messages can be transmitted also on edges that are not currently alive?
Yes, so we could, so maybe that's something we should do, yes. So maybe we should not just stick in the components. Yeah. And in fact, you're already way ahead. So that's what we're going to do next. Yeah. So, first of all, if you say the component, it's not going to be order d, it's going to be order d of the component, which might be as bad as n, even if the diameter of the graph is small, and that makes our kitty very, very sad. So, not good, because n log n is trivial, right? That's a linear number of rounds, that's boring. Okay, cool. Before we try to get solutions, let me first give you kind of a brief overview of what's actually known. So the first result that actually works, that gives something non-trivial, was by Kutten and Pelik. It's a celebrated, somewhat complicated algorithm. It achieves a running time of square root of n plus d. Okay, so that's better than linear, because for small diameters, this is square root of n instead of linear, which is clearly better, quadratically better, but it's still not really great, right? If you think of d as poly logs, then the running time is still going to be dominated by the square root of n, and it's it's somewhat slow. So people were not happy and tried to improve this, and then turns out that you cannot really improve over it. In fact, there's a square root of n lower bound, and over time we understood this lower bound better and better, and it's really a dooming lower bound in the following sense. This lower bound applies to almost any non-local network problems that you can think of. So local problems, of course, we know are a different thing, but if you have, so even the simplest non-local problem is going to have the square root of n lower bound in the running time, even if you want approximations, right? So clearly there's some completely trivial approximations which you can answer without even looking at the graph. If you want anything slightly better, square root of n lower bound applies. The counterexample graph, it's not that complicated, but I don't have the time to quite show you, but the diameter is really small. So it's a graph that has logarithmic diameter, And still on this like really tiny diameter graph, it's going to take square root of n time. And this lower bound is an unconditional lower bound. And basically it reduces to the communication complexity of disjointness. Right? So, well, to some extent, as a theoretician, we can dance and be happy because we now have an optimal algorithm, right? So there's a square root of n upper bound in algorithm, and we have a lower bound of square root of n, and life is great, right? Except, yes?
The lower one is also for randomized protocols as well.
The lower bound is also for randomized protocols. Yeah, randomized approximation, whatever you throw at it, it doesn't help. But I argue, I don't know, I'm not happy with this. And I'm sure, if your boss would come to you and say, look, I have this distributed network, I want you to compute an MST. You think about it, you come up with an algorithm, you're like, boss, I have a really great algorithm, it's an optimal algorithm. Your boss runs it, it takes square root of n time. Super slow. So he's frustrated, he comes to you, well, what happened? You said it's an optimal algorithm. You say, well, look, there's a different network, not the networks that I'm having here, where I'm actually running the algorithm. There's a different network with the same number of nodes, with the same diameter as our network. And on this different network, no algorithm can do better than the algorithms that I gave you. He's not going to be happy with this, right? I mean, in fact, if you look at the kind of lower bound graph, it's a completely artificial graph. No network in the world looks like this, and even more, anybody who knows this kind of stuff, I've not seen a single person who would come to me and say, I believe that if you take a network that's out there in the wild, has the characteristics that this lower bound applies. So yes, there exists some really bad network, but it's really not the network that we're interested in, right? And in fact, if you run the Kuttin-Pelek algorithm on any network, no matter how nice it is, it's always going to take square root of n time. It's not going to sometimes run faster, sometimes slow. It's always going to take square root of n time, no matter how nice the network is, right? So for me, this is really not the end of the story. This is really where our story begins. So let's try to do something better, right? Something provably better. Let's try to do some nice math and come up with some algorithms that are better than square root of n plus d. Okay. And so here's the key problem, which turns out really underlies any of these non-local algorithmic problems that you want to solve. This is the one problem that you really need to care about. It's a simple problem. We have essentially seen it before. I call it part-wise aggregation. So it takes a network. So I give you the network, and I also give you some connected subsets, an arbitrary number of them. The only condition is that all of the subsets are connected. And I want to solve some very simple aggregation problem. Every node has some value, and I want to compute a very simple function, aggregate function, on the values for each of these connected subsets. Right? So this is exactly the problem that we had for MSTs. There we had connected components, they're connected. Every node knows the value of its outgoing edge, and we just want to compute the minimum. Right? So it's exactly this problem. And of course, so what's the problem here? If we want to compute this, the problem is, of course, the challenge is the diameter of these parts, of these connected subsets, they're chosen adversarially. We have no control over them. So these diameters could be much, much larger than the diameter of the underlying graph. Okay, so that's the challenge. And if you think, oh, I'm just telling you basically exactly the problem that comes out of MST, that's true, but I want to argue that this is actually a common problem that will pop up in a variety of settings. In particular, if you have any divide and conquer style algorithm will have this type of problem. Right? In the divide and conquer, you have some subparts of the network. You want to compute some super simple function on these subparts of the network, and you want to do this in parallel. Yeah?
Is the requirement of connectivity for subsets essential?
Yes. Yeah. Otherwise, you could have otherwise it might not be avoidable that there's tons of congestion. Yeah. Okay. So if you think of divide and conquer, right? If parts that you divided on that you want to compute stuff are not even connected, then at least you wouldn't be able to run distributed algorithms on these disconnected parts. So yeah, so this is a natural problem. And this is an informal claim, but I really want to claim that this super simple pairwise aggregation problem really captures the crux of what makes problems hard. In particular, if you cannot solve the pairwise information aggregation problem fast, then you cannot really have any optimization algorithm run fast, and vice versa. If this one is fast, then you should be able to do basically most or any kind of optimization algorithm, you should be able to solve them fast. That's an informal claim, but that's kind of the right intuition. Okay, so let's go where exactly you suggested. Let's try to solve this problem. And okay, so low congestion shortcuts is basically the tool that's going to come out of this. But as you'll see, it falls out very, very naturally, right? So what's the problem? The problem initially when we tried to solve these things is we just stayed within the subset, right? So we had this long windy path, and we wanted to compute the minimum, and we were just saying, well, flood within the subject, so stay within the subject, and then the diameter is very long, and we have a problem. But instead, what we should do is use some extra edges, right? So if the diameter has a short, if the graph overall has a short diameter, then there should be a short path to come from one end to the other. So let's use some extra edges and use some extra nodes just for the communication, right? So that's what a shortcut is. Okay, so here's the key definition of what a low congestion shortcut is. We say a shortcut has congestion gamma and dilation, so it has two parameters, a congestion parameter and a dilation parameter. And what it does is for any set, any of these connected subsets, it defines some edges and some nodes that I'm allowed to use in the communication. Right? So I'm gonna, if this is my S4 set, which is a long and windy path, I'm just gonna give it these H4 edges and nodes to help with the communication. Okay, so I'm sure you can figure this out. So there are two properties that I want from these low congestion shortcuts. What are these two properties? Yes, so one thing that we want is that if I have a set and I add the shortcut edges to it, then the diameter should be small, right? That's the whole point of the shortcuts. So clearly that's one thing. So why is this not quite enough? Because of congestion, right? So what's kind of the right condition to avoid congestion?
Number of parts you participate.
The number of parts that participate.
Is bounded. Each edge but doesn't participate.
Yes, each edge should not participate in two. So each edge should not be used by too many parts. Because if one edge is used by all the parts or many parts, then clearly they're going to have to wait for this edge. It's going to take a long time. So yeah, so this is a fairly straightforward definition once we have understood the problem. So the two things, once I add the extra edges to it, the diameter should be small. In particular, we call the diameter the dilation delta, and every edge should only be should be used only gamma often, right? And so we would like to make gamma and delta small. Makes sense, right? Are there questions about the definition?
So it's delta, not delta times D. The dilation.
Yes, and so delta, I guess, has to be at least D if we have a bad subset, because, yes, it's absolute. It's not a fraction. Okay, cool. Okay, so I claim that if we have one of these shortcuts, if you have one of the shortcuts, then we can actually solve the pairwise aggregation problem reasonably fast. So anybody who did not already see the answer, did everybody see the answer already? That's unfortunate. Okay, yeah, then I'm just going to give it away. So I claim that if we have a shortcut with dilation delta and congestion gamma, then we can actually solve the pairwise aggregation problem in gamma plus delta time. Okay, I think gamma times delta is really trivial. Does anybody see how to do gamma plus delta times some logs? We're hiding logs here everywhere. Priorities, I don't think priorities would necessarily do it. Yeah, so it's, so you know, it's a little bit more of a big hammer than we need, but so, okay, so there are two parts to it. A, you have to decide how to route the packets. Okay, here we're just gonna do something very simple. Let's compute, you know, a BSF tree on each of the things, and we're just gonna broadcast and aggregate along this tree, right? So for the routes, we're really doing nothing fancy. Makes sense? I mean, we have the part and we have subsets, and we're just going to compute the total diameter delta. We're going to compute some tree of diameter delta on these things, and we're just going to use those edges. Okay, so that's the routing part. For the scheduling part, this is kind of, I guess, the first time I've seen it is like implicit in latent max Rao, but it's just a much, much simpler version. So here's kind of a neat trick. What we're going to do is, instead of just doing everything at once, and then we might have congestion of gamma at an edge at one time, we're just going to use a random delay, right? So instead of starting all the broadcasts at the same time and potentially being unlucky and having one edge really congested, we're just going to give each of the broadcasts or each of the aggregations a random delay between 0 and gamma, okay? So if we do this, what's the expected congestion in any particular round on any particular edge? 1, right? So the expected congestion, at most gamma of these use it, but now each of them has a random delay. So in expectation, there's going to be only order 1 guys who want to use the edge at the same time, right? And we can throw in an extra log n for good measure, and then we get concentration results, and with high probability, no edge will have a congestion in any point of time that's larger than log n. Does that make sense? Awesome. Yeah.
Random delay is required to make the buffers not be overall time. Overall time would be good if you do any greedy.
I don't think so. I don't think so. But
It's exactly the problem they dealt with.
latent max Rao deltas. Yeah, they need to use. It's slightly different because here we have trees. They look at path. But we're willing to throw an extra log in at it. They actually get really delta plus gamma times a constant, which is actually not, I'm not sure if that's possible here.
They got it with 1. They got it without it.
They got it without the log, but they do it only for path. Yes. So log is easy. In fact, I don't know how to do it for trees without the log, and I know it with an additive polylog. I'm happy to talk about this, but it's kind of a sidetrack. Okay, cool. So this works, and the extra log n, we really don't care. Sweet. And then once we have expected congestion at most, maximum congestion log n, then what we can do is, you know, we basically just need delta plus gamma meta rounds. In each of them, we might have log n congestion. Each meta round is going to be order log n real rounds. And so the total time is just going to be delta plus gamma times log n, which is exactly what I claimed here, right? So it's much simpler than latent max Rao, no Lowish local lemma, no nothing involved here because we just throw an extra log in it. And also this is distributed. We don't have to, the other part would not be distributed, right? Okay, cool. So this is simple. So delta plus gamma is what we get. So this is really the parameters that we care about.
Do you need the randomization?
One can get deterministic results as well. Yes, I'm going to get to that later. But for now, randomization is fine. Yeah. For this, the easiest thing is to use randomization. Okay, cool. So this was our shortcut definition. And we know that they can do this in delta plus gamma time. And so really, we call the quality of a shortcut is basically just delta plus gamma. Okay. Cool. So let's look at some trivial bounds on. Let's look at some trivial bounds on the quality of shortcuts. Okay. Who can give me some parameters for delta and gamma? Trivial, really trivial. What is possible? 1 in n, right? So with a 0 congestion, or a congestion of 1, and a diameter of n, that's possible. I just need to do nothing, right? Very good. Okay, I love this. Another one. Maybe one where the dilation is good, but the congestion is bad.
Everything contains elements.
Yes, so if I just give every subset the whole graph, what's going to be my dilation? D, right? What's going to be my congestion? N. Pretty bad, right? Okay, I mean, these are trivial, but good. So the quality of both of these things, unfortunately, is N, so that's not good. So here I claim that we can also get something that's just a tiny bit, little bit less trivial. I claim we can also get, always, for any graph, we can get shortcuts with square root of N congestion and square root of N plus D dilation. So the quality is going to be square root of N plus D. So that's just a tiny little bit less trivial. Does anybody see how that's possible? So here, the dilation that we're shooting for is square root of N plus D. Right, so let's ignore the D, square root of N. So which parts do I really have to shortcut?
Only low degree.
Not degree, but
Diameter rather than log N.
yeah, if I have a part, exactly. So I'm just going to say it so that everybody hears it. If I'm shooting for a dilation of square root of N, and I have a part that doesn't even have a diameter of square root of N, I don't need to shortcut it, right? It's already short enough. So those things I don't need to shortcut. So I really only need to shortcut subsets that have a diameter that is larger than square root of N. Now, how many of those can there be? Square root of N, right? Because each of these parts needs at least square root of N nodes. There can be at most square root of N large parts. If for each of these parts I give them the whole graph, so this is really, just a mix of these kind of two trivial strategies, I'm fine, right? I have a congestion of square root of N, and I have a dilation of square root of N plus D. Awesome, cool. So this gives us for any graph, we have something of a quality square root of N plus D, and really there's no magic behind it. It's really, like large parts get everything, small parts are on their own, and that's perfectly fine. So it's really not much behind it. Right, cool. But I claim this already gives us a really nice and simple square root of N plus D MST algorithm. Right? So I'm just going to use these. I'm going to run Brewster's algorithm. Start with repeated log n times, and in every round I have these connected subsets, and I compute a low congestion shortcut for it. Okay, that's a fancy way of saying, in this case, if I just want to shoot for square root of N, what does it mean? I'm just going to look, is a part square root of N large or small, smaller than square root of N? If so, just aggregate within the part itself. Take square root of N time. I have this time, I don't care. Right? Once, after square root of N rounds of everybody being on their own, there are at most square root of N parts left. And for those, I can just use the whole graph and flood all the information in the whole graph about these square root of N subsets. And we're done, right? So aggregate the cost and identity of the cheapest edges, add the edges to D. We only need log n iterations, and so the running time is basically Q times log n. And if you do the random delays, then we have another log n. For these really trivial shortcuts, we don't need random delays. It's fine. But this gives a really nice and simple explanation for kind of a square root of N plus D algorithm. Much, at least intuitively and kind of conceptually, much simpler, and also it's a nice algorithm. Well, generally, this also means that it can't be better shortcuts than the trivial ones that we gave, because if for any graphs there are better shortcuts, we would get a better MST algorithm here, and we would beat the lower bound, and that would be a problem. Right? So in general graphs, this is the best we can do. This is a very simple and cute algorithm. But the good thing about this is that if there exists a better low congestion shortcut and we know how to compute them, this algorithm is going to be faster. Right? Okay, so now the question is, well, are there some networks? Which network? I mean, I was claiming that most practical networks are going to have, faster algorithm, better shortcuts. And well, the question is, of course, how do you model these things? So, as a theorist, let's pick some nice family of graphs and try to show that hopefully they have some some better shortcuts. And so the first results that we had are for planar graphs. Turns out, so in planar graphs, for example, any planar graphs, and for any set of partitions, there exists a shortcuts with d log d congestion and d log d dilation. Right? So the quality is going to be d log d. It's almost going to be diameter. And this is going to give us an order d tilde algorithm to solve MST in planar graphs, which is cute. Right, so okay, there's two things. A, these shortcuts exist, right? That's important. B, also in order to be useful for us, we need to be able to compute them, and we need to be able to compute them fast. So in fact, also if these shortcuts exist, then they exist, and if you have a planar embedding, then there exists an algorithm that computes these in order d time. So that's great. And a planar embedding can also be computed in order d time. And that was actually quite a tour de force to make that happen. I went back to my very, very, very first results that I ever had in my life with Bob Tarjan on a simpler, more general linear time planarity test, and we made it distributed, and it worked out in order d time. It's a nice work. But so this is not quite as simple as I wanted it to be. But in order d time, we can compute an embedding. Once we have the embedding, we compute these nice shortcuts, which we know that they exist. And then we have a faster algorithm. In fact, the log d that's here, this is actually also tight, at least up to a log d. So there are some planar graphs in which you cannot get exactly d quality d. You need to have d log d, at least over log d. Awesome. So what we get from this is order d round distributed algorithms for minimum spanning tree and many other problems. And I want to give you a little bit of at least some insight in how this works. What's my time?
20 more minutes.
20 more minutes, perfect. Good. Okay, so here's a slightly simplified theorem, and I'm going to sketch it for you. It shows all the essential ideas. It loses a square, but for us it's fine for now. So I'm just going to sketch for you why planar graphs has shortcut with order decongestion, order d squared dilation. Okay. So here's a shortcut definition. Fix any BFS tree. So we compute a BFS tree and fix any planar embedding. And then each part has a leftmost and a rightmost node in this embedding. Right? So if you look at the pictures, this is a part, this is the embedding, and this is our tree. Then this is the leftmost and this is the rightmost node of the blue things. This is the leftmost and rightmost node of the yellow part, and so on and so forth. And the shortcut is defined as follows. The HI, the edges that we allow each of the ith part to use, so the edges that we allow, for example, the blue part to lose, is anything that's enclosed. So if I look at the leftmost point and the rightmost point, in the tree, this closes the cycle, right? This is called a fundamental cycle. Anything that's enclosed by this fundamental cycle, not the border itself, anything that's strictly inside the cycle, in the planar embedding, these edges, the blue set is allowed to use to communicate. Okay? Is the definition of the shortcut clear? Cool. Yeah, so that's the definition of it. So yeah, so the blue one is allowed to use all of this, the red one is allowed to use this, the yellow one is allowed to use anything that's closed in here, and so on and so forth. And okay, so we need to prove two things, congestion and dilation. Okay, so let's first prove that the congestion is small. So what I want to say is, for any edge in here, there are not too many colors, there are not too many sets that are allowed to use it. Okay, and so here we're going to use the planarity of the graph. Basically, in order for an edge to be used, there needs to be a set below it. And you can define this rigorously in a planar embedding, what below means, so that it's enclosed by the set. Okay? And this here, this is a BFS tree. So the depth of this tree is at most d. Right? So there can be at most d sets which are strictly below each other. It's fairly intuitive, and one can make this formal. So there can be at most d sets that are below each other in a depth d tree. And so every edge can be used by at most d of these sets, right? So this gives us congestion. If you look at dilation, then basically I want to say if I have one point in the set and I have a different point in the set, I can give you a path that uses some of the edges that it's allowed to use, and this path is of length at most d squared. Okay? So here's what we're going to do. If we look at the enclosed parts here, the border itself I'm not allowed to use, but anything in here I'm allowed to use. These are trees, right? These are kind of subtrees that I'm allowed to use. So what I'm going to do is I'm currently in a certain subtree. Let's say I'm here. I'm just going to walk up and down this tree in such a way to come out as far as possible on this green path that I want to traverse to the right as possible. Right? So I'm just going to walk up and down the current tree that I'm in to go to the point that's the furthest on the green path that I can go. If I'm arrived here, then by just using these shortcut edges, I can't go any further. So I'm going to do one step on the green path itself. And this is going to put me into a different tree. Right? Because if it wouldn't have not put me in a different tree, then I could have used this tree to go even further. In this tree, again, I'm going to walk up and down to go to the furthest point. And it's clear that we will never come back to the same tree. Right? Because if at some point I end up in this tree again, then I could have already shortcut along this tree in the very beginning when I visited it the first time. So what's the total length that of this kind of shortcut path? Well, how many of these trees can there be? Well, this is a BFS tree, so the length here on this part is, well, d2d. And every time I go up and down this tree, this is again a subtree of a BFS tree. So this is going to be at most up and down is also going to be at most 2d. So overall, this path is going to be at most d squared long, or 4d squared or something like this. Does that make sense? Cool. Yeah. And if you want to get d squared down to d, you need to selectively give some parts on the boundary here to the shortcut itself, and then you can get d log d, but I don't know. I'm not sure if that's interesting enough to dig into this. So, cool. Okay, so let me, so these are all the proofs and things that I wanted to show you. So let me just tell you a little bit in the remaining time what further results we have on all of this. So, yeah, simple definition, we just say network has a good shortcut if the quality of the shortcut is roughly its diameter, right, up to polylog. So planar graphs have good shortcuts. Graphs with small genus, bounded genus, or polylogarithmic genus have good shortcuts. The proof is very similar to this, to what I said before. You can generalize this to bounded genus graphs. Graphs with bounded paths with networks with bounded tree width, all of these have good shortcuts as well. One thing that's nice about genus is it makes, many networks in practice are somewhat planar, but they're probably not exactly planar. One nice thing about a bounded genus graph is if you take a planar graph and you add a few bridges, a few extra edges to it, it's not going to be planar. But any edge can increase the genus by at most 1. So if you don't add too many edges, it's still going to be a bounded genus graph. So that's a much more robust notion. Another thing that actually sounded really simple in the beginning but turned out to be technically really, really difficult is all of these graphs are also robust under adding extra nodes. Okay, so if you take a bounded genus graph, it has good shortcuts. If I take a few extra nodes and connect them to whatever I want, it's still going to have good shortcuts. Right? And what makes this so tricky is that shortcut actually can't get much worse. But what can happen is that if I add one extra vertex that connects to as many vertices in the graph already there, that's already there as I want, then the diameter can go down a lot. Right? And if the shortcuts are the same, but the diameter goes down, suddenly these shortcuts are not good anymore, because good means you're competitive with the diameter. So in fact, by just adding a single vertex, you might have to completely, if the diameter goes down, you might have to completely rearrange and change the structure of the shortcut to be competitive with a new diameter again. which makes this result actually fairly tricky to prove. So you really need to use the bounded genus passes retrievers property here to make this statement true, to prove it. And in fact, for general networks, it's not true. So there are some networks which have good shortcuts, and you add one vertex to it, and suddenly they actually don't have good shortcuts. So this is not true in general. Here's another nice composition result. If you have a couple of networks that have good shortcuts, as many as you want, and you glue them together using what's called a clique sum, the resulting graph also has good shortcuts. So anything that's any networks that's modularly built from networks that are good using clique sums is also going to be good. One thing that we managed to prove recently is that, in fact, excluded minor graphs, which encompasses anything that we have seen before. We can't quite prove that they have good shortcuts. What we can prove is they have d squared shortcuts instead of order d shortcuts, which, if d is polylogarithmic, it's still going to be polylogarithmic, so that's good. The right answer should really be order d, but we don't know how to prove it. So anything that's minor closed, that excludes a minor, is also going to have good shortcuts. And that's a really, really, really large family of graphs, right? So this proof uses Robertson and Seymour's graph structure theorem, which basically, this is a huge monster, 23 paper, 20 years of work, and we just use it as a big fat hammer to make this happen. So what it basically says is that any graphs that exclude a certain minor can be decomposed as graphs that are almost as a clique sum of graphs that are almost embeddable. And almost embeddable means that they embed into some constant genus surface, and I get to add some extra vertices to it, and I get to add some extra vortices to it. And believe me, you don't want to know what a vortex is. It's a nasty thing. But so you can already see clique sums. We had adding vertices. We already had bounded genus. We had, and so combining all of this together with the theorem is still a whole lot extra work, but that's roughly how we prove it also for excluded minor graphs.
Can you do it in distributed way?
Good question. Okay, so these are all existence results, right? And in fact, in the beginning, for planar graphs, we had this really complicated algorithm to produce. We needed the planar embedding, and we had this complicated embedding algorithm. And I don't know how to do it even for like embedding on a torus. I don't know how to do this distributedly, right? And these things are typically even sequentially, it's not clear if you can get a decomposition in a nice time distributedly. It would be hard. So no, yes.
Question about the families. All your families here were sort of graphs with bad expansion. What happens with expanders? Can you do it?
Expanders will be good. Expanders will be good because there are many different passes that you can use, so congestion will be small. Yeah. These graphs don't necessarily have bad expansion, right? I mean, depending on what you mean with expansion. Like a star is a planar graph. Yes. Depending on what expansion.
Something else like a real expander is it because you have many things.
Yes, expanders have good shortcuts, logarithmic shortcuts. Okay, yeah, so what about the algorithmic side? And so here's one thing that's really cool about all of these shortcut construction. It actually turns out that they don't just exist shortcuts, but they exist shortcuts which have a specific form. Basically, you can give me any low depth tree, and basically I'm only allowed to use these tree edges as my shortcut edges, and these shortcuts still exist. So we call these tree restricted shortcuts. And in the planar case, for example, this is exactly what we did, right? We started with a BFS tree. I only ever used BFS tree edges as shortcut edges, and still a shortcut exists. So this is true for all the shortcuts that I've shown you. They are of this form that they exist for tree restricted shortcuts. And it's actually a simple result, but this really made this whole framework much, much more powerful. So there's a fairly simple natural algorithm, approximation algorithm to compute the approximately best tree restricted shortcuts. So I don't need to know, is this a bounded genus graph? Is this an excluded minor graph? What kind of property does it have? All I need to know is, or I don't even need to know, is that there exists a good shortcut with a good quality, and I have a distributed algorithm which will compute, and that this shortcut is tree restricted. And there's a distributed algorithm which recovers and computes the best shortcut up to logarithmic factors in quality of the shortcut time. Right? So you can really run this. You don't need to know the structure. You don't need to know why it's a good network. You're just going to run this algorithm. It's going to find you the best shortcut. And then you're going to basically have an algorithm that's going to run as fast as it's possible for the given topology. You don't even know why it's going to be running fast. Mathematically speaking, what's the property that makes it run fast? But it will run as fast as it's possible for this topology. So that's a very cute result. And then also to answer Noam's question, can we do it deterministically? The answer is yes. And also, recently people have started to care about message complexity again, like how many messages do I need to send? And, I guess Potsi best paper was, MST with linear number of messages and square root of n time. Turns out very, very easily you can make shortcuts run in order m messages, pairwise aggregation in order m messages, right? And so that automatically means any algorithm that uses shortcuts, you can, if the underlying algorithm is deterministic, you can make the shortcuts deterministic, and you can make the message complexity linear, or near linear, which is the best that you can hope for. Right, so that's also kind of a cute result. And then, there are a bunch of problems to which we then applied this. So it's not just MST. Here I've always used MST as one running example, but you can get a min-cut algorithm, 1 plus epsilon approximate min-cut algorithm. You can get various types of shortest path approximation algorithms that are based basically with the pairwise aggregation problem as a primitive. And so all of these are going to run in square root of n plus d time in the worst case, but in near diameter time on most graphs that we care. They're going to run deterministically if the original algorithm is deterministic, and they're going to run in this linear number of messages, which is nice. Good. So that's basically So if you put all of this together, there are many different kind of problems which you can use shortcuts for. And if you apply it, then basically it's always the same algorithm the part aggregation part is always the same. It runs a simple algorithm which finds the best shortcut. And, of course, if you have a worst case pathological super bad graph, it's going to run in square root of n plus d time. And that's optimal, right? Because in these graphs, well, we know that you can't do better. But if you have a good network, and for, large different classes of graphs, we can prove that they're good, but probably most networks that you will encounter in practice will actually not be of this pathological worst case form. On these graphs and networks, it will run much, much faster. It will basically run in diameter time. So this is kind of as instance optimal up to logarithmic factors, right? I mean, you can't do it on this given network. You can't do it in less diameter time. You do it in diameter time. You get linear number of messages, and you basically get algorithms that are as fast as they can be for the given topology. So let me conclude with kind of what's left to do. So it's a bunch of open questions. So there are still several fundamental optimization problems which we don't know yet how to solve them using pairwise aggregation. For example, can we compute a depth first search tree? Can we compute a maximum flow with pairwise aggregation as a building block? If so, then basically all the running times for special graph classes, the linear number of messages, and so on, directly carry over. What I would also really like to do is show this instance optimality and kind of show a reduction in the other direction. Right? So the pairwise aggregation seems like a much easier problem than MST, for example. The direction that we can prove is, the other direction. I mean, once you have pairwise aggregation, you can solve MST. But at least intuitively, this should be the easier problem. So if you could prove that pairwise aggregation is at least at MST is at least as hard as pairwise aggregation, then this would basically mean on any graph up to logarithmic factors, you get the best algorithm for this given graph, right? So that would be cool. So actually expanders are the only example where we know that there exist good shortcuts, but they're not tree restricted. Right? If you take an expander and you restrict yourself to a tree, it loses kind of all the nice properties that you want from an expander. So expanders have good shortcuts, but they're not tree restricted. So generally, it would be nice to have an efficient distributed algorithm that computes an approximation for not just tree restricted shortcuts, but any shortcut. Can we further characterize, I don't know, excluded minor graphs? Okay, first of all, we haven't proven it yet. So the vortices still give us a bit of a headache, so I would really like to prove that, excluded minor graphs have order D shortcuts. But are there more general graph classes than excluded minor graphs? So can we characterize kind of what makes a good network a good network? And yeah, that's all I have to say. Thank you so much for participating. Today. What about random graphs?
Planar graphs with some noise added, like less of epsilon and random edges.
Epsilon n random edges.
But then you don't have this particular minor.
So if you had epsilon n random edges, it's an expander. So that's good. If you add a small number of edges, then then it's still going to have a small minor. So it's also going to be good. Yeah, I don't know if you add square root of n edges to a planar graph randomly. I don't know. Yeah, good question. Other questions? Yes.
It seems like this technique would be useful for sparse graphs, whereas in dense graphs, intuitively it seems like it would be easier to find shortcuts.
Yeah, so I would assume that it applies to sparse and dense graphs. I guess most graphs that we care about tend to be sparse. All the graph classes the natural restricted graph classes that I know are sparse, like excluded minor graphs are sparse. But yes, I would expect that even dense graphs have, unless it's somehow artificial, nasty, pathological network, it should have good shortcuts, and then you should be able to recover them. I don't know of any, what's a mathematically nice graph class that's not all graphs and that's not sparse. Yes, so GNP is interesting, and then so then GNP is an expander. This should, we don't have any examples of a graph class that's dense that has good shortcuts, except for expanders. But that's more because I just don't know any, I don't know any good graph classes that are nice to deal with mathematically and are dense.